Okay. And so the question is to find the Taylor polynomial of degree 4 for this function here. And there are many ways to do this. So let me see the common way that I saw from the computation you guys did. The first way is to compute the coefficients of the Taylor polynomial by the direct computation, which is we compute f0, which equals to 2. We again, so this is method 1. Okay. To do method 1, we compute f0, f prime 0, which equals to cosine 3x plus or minus 3x sine 3x at x equals to 0, which equals to 1. Okay, and then we further compute f double prime 0, which equals to negative 3 sine 3x minus 9x cosine 3x. Then you have another minus 3 sine 3x. When x equals to 0, this equals to 0. And then you do the computation and so on, and you find all the coefficients. So let me actually finish all the computation here. So when you do it for one more time, you get actually negative 9 cosine 3x minus 9 cosine 3x and minus 9 minus x sine 3x. So this is going to be 27, sorry, and this is a plus. And then you have the very last term, which is going to be another minus 9 cosine 3x. Okay, and you evaluate this at x equals to 0, you get 27 or negative 27. Okay, and you do the same thing for the fourth order derivative, and you find this actually equals to 0. So what are these numbers? f0, f prime 0, f double prime 0, and f third derivative of 0 at x equals 0, and the fourth derivative of f at x equals 0. These are the coefficients for the Taylor polynomial in the following sense that we have the following formula. P4 of x, which is a polynomial. Remember that this is an honest polynomial we are computing here. So P4 of fx equals to f0 plus f prime 0 over 1 factorial times x plus f double prime 0 over 2 factorial x squared plus f triple derivative 0 at 3 factorial at x cubed plus f to the fourth power, fourth derivative at 4 factorial x to the fourth power, which equals to 2. This is equals to 2, and this equals to 0, right? Sorry, there must be, oh, actually it is right. So plus x, and we have another one, which is, this is 0, this is 0, so you have another negative 27 over 6 x cubed, which can be simplified as 2 plus x minus 9 over 2 x cubed. Okay. So what we are computing here is the best fourth degree approximation of this function fx. Okay, this is the best fourth degree approximation of this given function here. Okay. The reason why we say it's the best is that in the following sense, is that if you look at all the possible fourth degree polynomials, the error term between the given function, the polynomial, and the given function here will be minimized by this particular function here. Even though it looks like it's a third degree polynomial, but actually the best of fourth degree doesn't have the degree 4 term in it, actually. That's the funny part for this computation, okay? So this is the first method for doing it, is by computing all the coefficients and put into the general pattern, this general formula here for it. Remember, there's a factorial term involved. It's not just these numbers that determine the coefficients. Secondly, once you compute these, you only need to insert a corresponding degree, the x to the nth term to it. You don't have to do anything more than that. So no need to substitute anything with these. A common mistake would be using this to plug into the formula. That would be totally wrong. Okay, so this is the first method. So let me teach you another way to do this problem. So another way to do this is to find out, so method 2 is to first find out the Taylor polynomial, find the Taylor polynomial of gx equals to cosine x, the degree 3 polynomial, p3x of this function first. The reason why we are only interested in p3 is because, as you can see from the expression here, the function fx equals to 2 times x times cosine 3x. Suppose you can find the p3 term for these. Together with x, you're going to find the best fourth degree, right? So that's my strategy. Instead of looking at all the complex computations like these, what I want to do is I want to do a simpler computation only for this function, and then using substitution and also using multiplications and using additions, I can compute the P4 for this function. But to do that, all I need is to know the P3 for this function, okay? So let's do that. So what is a P3 for gx equals to cosine x? That's actually a simpler computation compared to our previous one, is g0 equals to 1. And g prime 0 equals to negative sine 0 equals to 0. And g double prime 0 equals to negative cosine 0 equals to negative 1. And then you have g third degree 0 equals to plus sine 0 equals to 0. Okay. And we don't need to compute the fourth term because that doesn't matter at all. We are only interested in P3 because we have this extra x here that's helping us to reduce the degree to degree 3 actually. So that means the best third degree polynomial P3 for cosine x of gx is given by P3x equals to 1 minus x squared over 2 factorial, okay, which equals to 1 minus x squared over 2, okay. With that said, now we know the Taylor polynomial for gx, then the question is, what's the Taylor polynomial for fx? Okay, so the first thing is, what is the third degree best approximation for cosine 3x is going to be given by 1 minus 3x squared over 2. Does it make sense? I'm just substituting x by 3x for this term here, okay? And now you have extra x, and you have another 2. So the P4x for fx is actually computed by simply adding 2 plus x times this, which is given by 2 plus x minus 9x cubed over 2. You guys see the difference?
Sorry, can you explain again how you got
Question?
from cosine 3x to 1 minus 3x squared over 2?
Sorry, can you see that again? I didn't hear very clearly.
Can you explain again how you got from cosine 3x to 1 minus 3x squared over 2?
Oh, yeah, so let me do that again. So the logic is the following. If we know the P3 polynomial, the best third degree Taylor polynomial for cosine x, and then what is the best third degree polynomial for cosine 3x is given by substituting 3x into what you just computed here. All you need to do to find the P3 for this function is by substituting 3x for x. And that's how I get 1 minus 3x squared over 2. Does it make sense?
Okay, and then the 2 and the 2 plus
is,
x comes from the other part.
The 2 and the x comes from the original form of the function, which is fx equals to 2 plus x.
Okay.
Yeah, because remember that what we are looking for is nothing but a polynomial, right? So to get the polynomial, 2 and x doesn't matter because these are polynomial, right? If you multiply polynomial with polynomial, you still get polynomial. If you add something, a polynomial to a polynomial, you still get polynomial. So all you need to do is to find the polynomial for this term only, right?
Got it. Okay. So
Yeah,
then
and
each term is 2 plus x times whatever, but you just pull it out.
Yes,
Okay.
yes, exactly. So that's how you get this computation. Yep. Okay, perfect.
Wait, so Bo,
Yep.
can you leave that up for half a second? And then also, I guess you knew to take the third polynomial, Taylor polynomial of cosine,
Yep.
because you have that extra x, that's going to give you that fourth degree.
Exactly.
Okay, because when you multiply that through, it's going to bring you up
to one more degree.
A degree.
Yep. Yes.
Understood.
Yes.
Thank
Indeed.
you.
Yep. That's the reason why I'm looking for P3 of cosine x only, without going too far actually. Okay, that makes sense. This whole thing.
Is there a rule of thumb for when this is going to work and when it won't work?
I would see that whenever you see cosine exponential function, sine function, anything that's actually composite with something inside it. For example, cosine 3x, exponential e to the 5x, sine to the negative 13x. Whenever you see something like these, using substitution is simpler than doing the computation itself.
Understood. And then,
yes, yep.
And then if
and then if you have any other polynomial, for example, suppose you are trying to, let me give you a actually more complicated example here. So suppose that you are trying to find, for example, let's see that the fx equals to sine 5x times e to the 3x. Okay, suppose our question is to find p, let's make it smaller actually, p3x. Okay, suppose we want to find out p3x. Okay, so what you need to do is you only need to find out, for example, there are many different combinations, but in order to find the p3 of this function, what you need to do is just to find the p2x of sine x and e to the x alone. Okay, because if you can find the p2, the second degree Taylor polynomial for sine x and e to the x individually, then you can substitute 5x and 3x to each of them, and then multiply those two polynomials together to get these.
Can you do this?
Yeah, let me do that. So what is p2x of sine? This is given by, actually, it's given by, I think it's x alone, actually, because they don't have a zero order term, they don't have the second order term. Only odd terms, odd degree appear. Okay, do you guys follow that? Why p2x of sine x equals to x? Just like the computation for cosine, you get sine x to the first degree when you differentiate once. I mean, yeah, let me actually be more explicit. So let me call this gx and this hx. So g0 equals to 0, g prime 0 equals to 1, and g double prime 0 equals to 0. Okay, because this is sine 0, which is 0. This is cosine 0, which equals to 1. This is another sine 0 equals to 0. Okay, so this is how I get p2 for sine x. Then what is the p2x of e to the x? Is given by, when you differentiate e to the x, you always get e to the x every time, right? So the p2 of e to the x will be equal to 1 plus x squared over 2. That makes sense? Okay, so suppose now you know this two Taylor polynomial, then what is a p2x of sine 5x? How would you do that? You substitute 5x for what you get in here. So that means the p2 of this is nothing but 5x. Okay, and similarly, the p2x of e to the 3x will be given by substituting 3x for each of the term here. So it would equal to 1 plus 3x plus 9x squared over 2. Okay, and that's how you get these. And together with these, we can compute the p3x of this combined function by multiply these two together. So we know that the p3 polynomial of fx is given by 5x times 1 plus 3x plus 9x squared over 2, actually. And the p3x of fx actually is equal to this, which equals to 5x plus 15x squared plus 45x cubed over 2. And that's how you compute something like this. Does it make sense? Okay.
Can you leave that up for 1 second?
Yep.
Thank you, Bo. So this is the alternative method. The other way you could do it would just be taking the derivative
Yes.
of
Yes.
x repeatedly, which is a pain in the neck.
Yeah,
Got it.
that's
Thank
correct.
you.
So that's why I see that whenever you see composite functions like sine to something, e to something, that's generally a hint that you want to do sine the exponential function first, and then using substitution to get the corresponding Taylor polynomial for that term. That'll be much easier. Yep.
Hypothetically, what if either sine was squared in this case, or
It doesn't
the
matter.
argument?
Suppose that in this case you don't have sine times e, but you only have sine to the 5x squared. Then you just compute the corresponding Taylor polynomial for sine. You substitute to get the Taylor polynomial for sine 5x, and then you square that. But so, for example, suppose you want to compute P3, then you better know P2 of sine first. And then suppose you get fourth degree term, you just drop that. You don't have that term. That
So
sense?
hypothetically, if we were doing a P3 for sine squared of 5x, you
Yep.
find the P2 for sine of x, plug in 5x, and then square it?
Yes, yes. So in this case, for
Okay.
example, it would be 5x squared actually. So it's 25x, which is the P3 for this function actually.
Thank you.
Yes, yes. Okay, does it make sense, this computation here? So the reason why we're doing all this Taylor polynomial computation is that in the very last section of this semester, you will be taught something called the Taylor series, which is for any given function fx, you are not going to compute just a polynomial. You are going to compute continuously an infinite series of polynomials like these. Okay, so if you didn't stop at any n equals 3 or n equals 5, if you just keep doing this, you wouldn't be getting a polynomial, but instead you would get a series, which is infinite many terms like this added together. That's called the Taylor series, which is the best, which actually equals to fx in some sense, and that's the most important thing for this whole trouble we are getting into, is to understand that how can you represent a function fx by an infinite series of power of polynomials. Okay, that's actually something we're going to teach at the very end of the semester. And so today is like April the 16th, so you guys have almost a month to learn to that point. And it will be very challenging, trust me. And there's many new concepts. So I would encourage you to read the textbook ahead of the schedule so that you can familiarize yourself before you actually see the lecture and before you do anything on the quiz on homework. Read ahead of time, because we don't have many time left for this whole semester. You really have to do it ahead of the time now, actually. Okay. So this is about everything I want to see about the quiz on Taylor polynomial. So the next thing is I want to see is actually about the difference between series and the sequences. So many of you actually made the following mistake, is that you confuse yourself from series and sequences. So let me take a very simple example, is pi. Pi equals to the following thing. So let me actually find the exact numerical value for pi. So, it's somewhere here. Okay. Yep. So pi equals to 3 0.14159265535 and 8973 blah 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 blah. Okay, so this is the irrational number, which is pi, which is the area of a unit disk, right? This is something we know. I mean, our ancestors know like 100 years ago, 1,000 years ago, I guess, in some sense. And the question is, what is the representation? What is the sequence? How do you represent pi as a limit of a sequence, and is different from how do you represent pi as the limit of the series? Okay, what is a sequence? If you're a computer science major, like I said, this should be very easy to understand. A sequence is just a list of numbers. Okay, so for example, if you want to have a sequence, a list of numbers which takes pi as a limit, the best way to do this is to have the first term to be 3, the second term to be 3.1, the third term is 3.14, the fourth term is 3.141. And you see the pattern here, right? And for this sequence, it's obvious if I'm taking the first n digits part of this number, this sequence will converge to pi. That makes sense? So this is how you represent pi as a sequence, a limit of a sequence. But how do you represent pi as a limit of the series? So what is a series? Kind of a slightly ahead of your schedule. So a series is a summation of a list of numbers. Okay. For example, in this case, if I want to have pi as a limit of a series, that would be the following: 3 plus 1 over 10 plus 4 over 100 plus 1 over 1,000 plus things like these. You guys see the difference? First of all, this is not a list of numbers, even though it's involving a list of numbers, which is 3, 1 over 10, 4 over 100, 1 over 1,000, and so on. This is a list of number underlying this series, but we are taking summations of the list of numbers in it. And this is the list, this is a series. And for this series, this one goes to pi. You guys see the difference is huge, right? This is very different from this concept. The series is very different from the concept of sequence, okay? So with that said, one of the questions I asked you guys to do yesterday is to write out the first 3 terms of a given series, of a given sequence. And some of you actually used the notation addition there in your answer, which is wrong, because you can see the difference here. For a sequence, there's no addition involved at all. It's just making a list of numbers there. Okay. But for series, you actually have additions. And what's the relation between these is that if you for a given series, if you stop at any first n summation there, you get something called a partial sum. A partial sum would form up a new sequence, which is approximately this. For example, in this case, if you call this the series S, if I let Sn to denote the first n term summation, then S1 would equals to 3, S2 would equals to 3.1, S3 would equals to 3.14, and the S4 would equals to 3.141. Then you see what's the relation. When you take the partial sums of the series, you actually get back to this sequence here. And that's why we want to understand sequence first, because when you have a series, when you talk about the limit of the series, you're actually talking about the limit of the series as the sequence of partial sums, which is these, the limit of these numbers. Okay, and that's the relation between series and sequence in this, the connection between these 2 concepts. Okay.
So S sub n right there, that's a sequence.
That's going to form a sequence. That's the nth term in a sequence. This is called a partial sum.
Understood.
Yeah, so this is the partial sum. Okay. So Sn, if you write in this form, n equals to 1 to infinity, this is a sequence now. And
it's a sequence of partial sums.
Exactly. It's a sequence formed by the partial sums, indexed by n. Yes. So you see from this example here, when you have the series S given by the infinite sum of digits of the pi, then the partial sum will produce the sequence as before, 3, 3.1, 3.14. And it is in that sense, we see that because when you let n goes to infinity, what does this mean? That means you're including more summations in the series, right? And the limit of that is in fact the same as the limit of the sequence for these partial sums. And that is given by pi. It is in that sense what we are talking about, the limit of a series. Okay. So with that mentioned, so let's go to the most important question is how do we determine if a sequence is converging or diverging? So far, I'll give you some examples. So let's do some more examples. The first type, there are many types. So the first type of convergence property is type 1, let me see, is rational expression. Okay. So what does this mean? By rational expression, I mean the following. Let me give you some examples. For example, suppose the general term for the sequence an is given by 3 plus 5n squared over n plus n squared. Suppose this is the nth term of your sequence. Let me make n equals to 1 to infinity. Okay. Then the question is, how do you find the limit of these kind of things? Then the limit when n goes to infinity of an, this is an example which I kind of mentioned last time, is that this is the same as talking about a limit of rational functions, right? When you have polynomials in the numerator and when you have another polynomial in the denominator, then the limit of this is totally determined by the coefficients of the leading degree term, right? So in this case, this is degree 2, whereas this is also degree 2. So the limit is given by the ratio of the two different, the ratio between of the highest of the coefficients of the highest degrees. So in this case, actually, this equals to 5 over 1, right? Which equals to 5. One way to see that is actually, if I want to write more details, this would equal to 3 over n squared plus 5 over 1 over n plus 1. How do we get these? We are simply dividing the numerator and denominator by n squared, right? When you divide n squared to the numerator, you get the 3 over n squared plus 5. When you divide n squared to the denominator, you get 1 over n plus 1, which has a limit to be 5 over 1, because when n goes to infinity, this term goes to 0. This term also goes to 0. So you are left with 5 over 1, which is this number here. So this is the reason why we're getting these. So for rational expressions, all you care about is the degree and their highest coefficients. Let me give you some more examples. If you have like an equals to 3 plus 5n squared over 1 plus n, then what is the limit of this sequence? As a sequence then, so limit in this case, when n goes to infinity, of an, which equals to limit n goes to 0, infinity, 3 plus 5n squared, 1 plus n. This actually goes to infinity, because now you see that the degree of the numerator is degree 2, the highest term, whereas the denominator is degree 1. What's the intuition behind that is that the limit of these two are determined by the rate of growth of the numerator and computation with the denominator. The denominator is like a linear function. It grows like 1, 2, 3, 4, 5, 6, things like these for the highest degree. But for the numerator, it grows like 1, 4, 9, 16, 25. You see that? So this one grows faster than the linear term, right? This can be also verified by using Lebesgue through, because when you differentiate both terms, this is like infinity over infinity. When you differentiate this once, this becomes constant. This one is still linear. So that's why this actually goes to infinity, okay? And vice versa, suppose it's 1 plus n that's in the numerator and 3 plus 5n squared is in the denominator, then this will go to 0, because the denominator has a faster growth compared to the numerator. And that's how you see, for rational expressions, that's how you determine its limit. It's the same strategy that we had before that we are using. So let me give you another more complicated example, slightly more complicated examples, which is given by n to the squared over square root 9n to the fourth power plus 3n minus 1. Okay, for example, if this is a sequence that we are looking at, okay, how do we determine the limit for this sequence here? Okay, then the question then is, what's the degree for the numerator? The degree for the numerator here is given by the second degree term. Okay, whereas the degree for the denominator is what? It's actually below the square root sign. So what is the degree of this term, of this square root of 9n to the fourth power plus 3n minus 1? Because the highest degree for whatever is inside the square root is given by this term, right? And then the square root of that is almost like 3n squared. Does that make sense? So that's why in this case, I can, intuitively speaking, this actually has a limit, goes to 1/3 as n goes to infinity. Okay. So this is the heuristic that I had, because I kind of understand what this one looks roughly like. Everything under the square root, when you apply the square root, roughly behaves like 3 to the n squared term. Okay, excuse me. And this gives you 1/3 as the answer. Okay. But how do you justify that? Is by taking the ratio of these things as before. So n squared over square root 9n to the fourth power plus 3n minus 1, and that equals to limit n goes to infinity, n squared over square root 9n to the fourth power plus 3 divided by n squared. This one divide 3n minus 1 divided by n to the fourth power inside the square root. Okay, because dividing n squared in the numerator and dividing n squared in the denominator doesn't change anything, but you can move the n squared in the denominator inside the square root, and that becomes n to the fourth power. Okay, so this gives you something like a limit n goes to infinity of 1 over square root 9 plus 3 over n cubed minus 1 over n to the fourth power. And that has a limit to be 1/3. And that's how you justify something like this in the for a question like this when there's the square root or cube root involved. Actually, it's funny that let me remind you guys, this type of question appear a lot in the final exam. Okay, so what I mean is that the ones involving square root or cube root, things like these, appears a lot in the final exam. So you have to understand how to deal with this by using this kind of dividing technique and doing the algebra correctly, and that's very important. Okay, so that's for type 1, which is about rational function. Oh, sorry for that. The second type is one you can apply L'Hopital rule. L'Hopital rule. Okay. So let me give you some more examples on this. I mentioned something like this, but I talked to Dr. Chadwick. It appeared that when he's lecturing on this, he didn't change from the variable n to variable x when you use the L'Hopital rule, which is kind of different from what I said last time, because for me, this is it's totally incorrect. I don't like it without changing the variable, even though it's a very formal thing, but I still just don't like it because n doesn't take value at any continuous number. It's just on integer values. You cannot differentiate that. But on the formal level, you can do it. So let's all agree, let's all just stick to Dr. Chadwick's convention that you don't have to change to the variable x. You just can directly apply L'Hopital rule to the variable n and you differentiate with respect to n. But keep in mind, when you do this, it doesn't mean it's reasonable, because you should be realizing that n is somehow changed into a new variable which actually takes all possible values, all possible real values. It's not just on integer values. And that justifies the computation. Okay. So it's the following. The first example is the following one. N equals to tangent inverse n over n. Okay. So how do we find the limit for this expression? And we do the following. When n goes to infinity, an equals to limit n goes to infinity tangent inverse n over n. When n goes to infinity, sorry, actually this one doesn't really involve L'Hopital-through, but what's the limit when n goes to infinity for tangent inverse n? This is something I mentioned last time. This is actually a very useful fact you should know for the final exam. So what is the limit when n goes to infinity for arctangent? Remember that the graph for arctangent is something like this. It's actually going like this, right? Okay. This is the graph for arctangent. And you can see that this actually approach to pi over 2 when n goes to infinity, right? So when n goes to infinity, this term goes to pi over 2, whereas this one goes to infinity. So the limit actually combined is just 0, right? Or you can use L'Hopital-through to help you with that, because another way to compute that, if you didn't know this fact that tangent inverse n goes to pi over 2, what you can do is, without doing this computation, you can jump over here to see that this actually equals to, when you differentiate the numerator and denominator together using L'Hopital-through, you get 1 over 1 plus n squared, which is the differential of tangent inverse n over 1, right? And this term definitely goes to 0, as you can see, because when n goes to infinity, this becomes 0 and this becomes 1, which is 0, right? This is another way to see that. So that's how you solve this problem using L'Hopital-through. Okay. So another example would be the following. So how do you do a question like this? Let's see that an equals to n to the nth power. And to do that, so limit n goes to infinity an equals to limit n goes to infinity. This is n to the 1 over nth power, right? And for this, we see that so this can be written as using the change of base. This actually equals to e to the 1 over n log n, right? Which actually equals to limit when n goes to infinity, e to the log n over n, right? A different way to rewrite these. But now, to determine the limit of this expression, this actually just equals to limit n goes to infinity of log n over n. Do you guys understand how I can jump from here to here? At this point, I'm computing the limit of this function as n goes to infinity. But to understand the limit of these, all I need to find out is what's the limit of this expression and apply to e, right? So that's the logic here. So how do we do that? We do the L'Hopital-through to the exponent, where you get actually 0, right? You can see it's 0, so this one actually equals to 1. Okay, and that's how you get the limit for this sequence here using L'Hopital-through. Okay, so this is everything.
Please?
Yep, sure. Okay, so any questions? Yep, that's everything's good.
Thank you.
Yep. So that's this kind of computations. Okay, so it's not very different from the L'Hopital-through we learned before. It's just applying to a different variable n in this case. So not formally speaking, it's the same actually. Okay, so that's the second part of the second type of finding limit of a sequence. The third type is something that you just learned. It's called squeezing theorem. which is a very similar to the squeezing theorem that you learned in functions. Remember that if you have a limit, if you know that fx is always smaller than gx and always larger than hx, if the limit of x goes to a, hx equals to limit when x goes to a of gx equals to capital A, then limit as x goes to a of fx would also equal to a. It's like you're forcing everything to go to the same point. So suppose you have two functions bounding this middle one, and if this two goes to the same place, let's call the limit here a, then the limit for the middle one has to go to a. That's roughly the intuition behind the squeezing theorem. Okay. So with that said, so how do we? Let me give you some examples of using squeezing theorem. I think that this is a topic that Dr. Chadwick has just mentioned. And let me find an interesting example here. I had one written before. Where is my example here? Sorry guys, just give me 1 second. I'll write something. Oh yeah, it's here. Okay. Oh no, actually, this is not one I have. Actually, let me. Oh, it's this one. Yep. So let's see an equals to 4 plus cosine n squared over root n. Okay. So how do we find the limit of this series, of this sequence? The first thing you should notice is that for cosine n, so if we just isolate this particular term, cosine n here, you should understand that, you should have an intuition that this expression doesn't go to anywhere. This one doesn't have a limit. This d and e do not exist. Okay. The reason for that is if you look at the graph of cosine x, when you look at the value of cosine x at integer values, they actually oscillates. Okay, so oscillates between -1 to 1. I mean, intuitively speaking, this is correct, but to actually prove this requires some effort. It's not that simple, actually. You have to understand how the integers, what's the value of cosine x at the integers, how they actually distribute. It's perhaps they all equal, maybe that's the case, and perhaps they're all very small, that's also the case. But to see that actually they oscillates with certain amplitude is very difficult to prove. This is something that's very interesting. I will leave this for you guys to actually to see if you can come up with some kind of a proof or evidence to support this statement. Okay, that'll be very interesting. Or you can run, if you can code, you can maybe write a program to compute maybe the first n sequence, n terms in the sequence, and let n goes to a very large number and see what's the pattern of that. Okay, and that's something I won't be able to prove here for you guys, but you should just keep this in mind. Also, similar results holds for sine n, so that's another thing which doesn't exist. If that's the case, how do we find the limit of this sequence here? That's where we are going to use the squeezing theorem, because there's one obvious squeeze that's going to occur for this one is cosine n squared is going to be smaller than or equals to 1 and larger equals to 0, right? Because of this, what we have here is n is smaller equals to 4 plus 1 over root n, but larger equals to 4 plus 0 over root n. Okay. On the left-hand side, what does it mean? This means that every an is larger or equals to 4, which is a sequence, is a constant sequence. It's a list of numbers which are all given by number 4. But on the right-hand side, it's a sequence given by 4 plus 1 over root n. What's the limit for this sequence? As you can see, when n goes to infinity, this sequence actually goes to 4 as n goes to infinity. And this one is always equals to 4. And because these two limits are the same, that means the limit of an in the middle has to be going to 4 because of this. Right? There's no room you can move between 4 and 4. Right? The only number that's between them is 4 itself. So that's how you squeeze to get your limit. That makes sense, this example? Okay. So this is about squeezing theorem. So it will be something. So I think the typical hint for you to use squeezing theorem is whenever you see cosine or sine n. Whenever you see a very transcendental expression like that, that's generally a hint that you are going to use squeezing theorem. Okay. But what I mean, of course, it's definitely not always true. For example, your sequence may be given by something like these. If an equals the cosine n times pi over n plus 1, what's the limit of these? Can someone just see that directly? What's the limit for cosine n pi over n plus 1? So first of all, what is the limit of n pi over n plus 1? When n goes to infinity. Or maybe n over n plus 1 times pi. This goes to pi, right? So this actually goes to pi. And hence, this whole expression actually goes to cosine pi, which equals to, what's cosine pi? It's -1, right? If I remember correctly. Okay, and that's how you find limit for these. You can see there's no squeezing theorem involved, but that's the point for me is that you have to differentiate from case to case. I mean, based on the situation. That's purely from experience perspective. You have to solve some questions to gain experience, which method you want to use, and to each individual sequence to find the limit. Okay. Okay. So that's example on the third type. Now we come to the very last example I want to mention today. Is actually something that's involving factorial. So let me talk about the following example, which is the very important example for future application. Is that what's the limit of this expression? Or maybe something like -3 to the nth power over n factorial. Okay. The reason why I give you these two examples, or maybe just one example in essence, is that the point is you have to gain some experience about which one is larger. We won't be able to really quantify how large each one behaves. That's something that's called involving a formula called Stirling formula that we will be learning if you are going to move on further to more higher mathematics. But for current understanding, you actually have to understand which one is larger for these two quantity. I mean, this is 2 to the n is like exponential growth. I mentioned to you guys, this is probably the fastest growth you can ever have. But in fact, that's not correct true because now you have n factorial. So let's look at what's the behavior of these. What is n factorial? So what is a1? a1 is 1 over 2. a2 equals to 2 times 1 over 2 times 2, right? Still, this one seems to be like a smaller than 1, smaller than 1. But what about a3? a3 is like 3 times 2 times 1, which over 2 times 2 times 2. And then you have a4, which equals to 4 times 3 times 2 times 1 over 2 times 2 times 2 times 2. Okay. And a5, you can keep going, and you have 5 times 4 times 3 times 2 times 1 over 2 times 2 times 2 times 2 times 2. Only these two terms, you get something smaller than 1, right? Every term afterwards, you can see the ratio is always larger than 1. right? Imagine if you keep going, let n goes to infinity, you have more and more terms that's very larger than 1. When you multiply them together, this number, this sequence will be growing to infinity, actually. Does it make sense? So actually, limit when n goes to infinity of an equals to n factorial over 2n actually goes to infinity from this writing here. That's the key fact I want you guys to at least memorize at this point, is that n factorial grows much faster than exponential grows. From that logic, you can see that the limit of -3 to the nth power over n factorial actually goes to 0, because the factorial is actually in the denominator. So that's why you get 0 in this case. Okay. So from there, we have this expression, and that's the very last example I want to do today for our discussion. So let's move on to the worksheet part. So let me give you out to the question I wanted to do today, which is, let me find it out, and put it on the screen. Okay. So what I want you guys to do today is the following question. This one. Okay, let me share screen so that everyone can see that. Okay. Try to work on problem number 2, and also work on problem one also. So 1 ABC and 2 AB is what we are trying to finish today for today's discussion. Does that make sense? So let me write it out. So the reason why I want to work on 2, actually, 2 is more important, is that this is actually one of the final exam questions from 1 year. So to give you a sense of ideas what kind of final question may look like, I mean, this is one of them. So you should definitely work on these. Okay. Is that clear? Okay.
For 1A,
yep.
What's the difference between A sub n and A sub n plus 1?
That's just the nth term in the sequence and the n plus 1th term in the sequence. So this is purely formal. It's like you're shifting the index. Suppose that you have a list numbers. The sequence an plus 1 is you forget about the first term, and you look at only the second term. So let me make an example. For example, if your sequence is like 1 minus 1 plus 1 minus 1 plus 1 minus 1 is the following one, right? This is a sequence. So what is the new sequence an plus 1? What's the very first term? When n equals to 1, for the original sequence, this one is 1 minus 1 plus 1 minus 1. But when you start from the sequence an plus 1, for n equals to 1, you actually start from the second term. So the new sequence an plus 1 is the following. Just by definition. You see the difference?
Thank you.
Yep. But they have the same limit. Roughly speaking, the sequence an plus 1 is by omitting the very first term in your original sequence. You can change the question to be, if you start from any place, finite place, if you omit the very first n terms in your original sequence, and you get a new sequence, does the new sequence have the same limit as the original sequence? The answer is yes. Just try to see why this is true to you, intuitively speaking. You don't have to give a very rigorous proof, but you actually have to understand the fact that this is true from the intuitive perspective. Let me see, someone send me a chat. Let me see. Actually, yeah. So yeah, work on these two problems, and they are important because they may appear on the next exam. So that's why I'm saying this. It's not because, yeah. So we already turned in something from on Tuesday, and that's it. I don't want you guys to work on everything on the worksheets because the other questions are totally irrelevant for the exam purpose. Okay. Okay, so once you have this, let me stop sharing and let's move back to, yeah. So stop me whenever you have a question. I can answer your question on these two problems. In particular, the question number 2 is kind of tricky in the sense that it's a funny question. Yeah.